Hi, this is Kumar Singh from Design Analytics LLC, and you're watching another episode of Maverick Mondays. We continue our brain-computer interface journey. Right? This will be the last episode, as promised in the previous one, where we will focus on the brain-computer interface. Right? So, as we discussed last time, we are going to look into a futuristic architecture of how a way in which a device may be embedded in the human brain to provide us smartphone capabilities, hands-free smartphone capabilities, right? As mentioned in some of the previous episodes, I'm not sure there is too much utility at this moment, but maybe things will change in the future, right? Now, before we look into the architecture, there are two key areas that we need to discuss, right? One is, what are the current constraints because of which I'm saying that this is mostly futuristic, right? The most important one is that our brain, human brain, has not been studied to a level where we want it to study in terms of the minutest details of all the cortexes, all the lobes of the brain, and how they communicate with each other. So we have a good idea at this moment, but not the level of understanding that's needed to incorporate or to make basically the dream of having that chip being embedded in brain come true, irrespective of whatever architecture is used, right? This will, in my opinion, continue to be an inhibition. One of the reasons that I think for next couple of decades this will not become a reality. One is that we have studied brains, right? It's mostly has been done on other species, and when it has been done on humans, it has been done on people who have certain level of disabilities, right? Because human brain is such a sensitive part of the body that if we end up making a mistake in a healthy human while studying their brain when they are alive, which is the most important aspect, right, in this kind of research, we may end up doing something to the quote-unquote wirings of the brain, right? So that's why it's not practiced anywhere in the world, I think. In healthy individuals, governments may not allow that, right? So it becomes kind of challenging. It's a challenging constraint on the path of developing the full understanding of the brain that we actually need to build this kind of capability that we are going to discuss. And then the second inhibition constraint, not exactly inhibition, the second major constraint is hardware, right? Considering the current form factor, too bulky, designed around people with disabilities, right? So it has to be rethought if we want to transform that into workable devices, right? Now, the second key area that we need to understand is, okay, when we say we want a smartphone embedded in a human brain, what are the capabilities that we are looking at? So far we have been discussing or like thinking about it in terms of if you go to the last example in the previous episode, we thought about it in terms of, okay, you think and things will happen on your phone, right? Or the same workflow that you can create on your phone by interacting with your hands, you can actually kind of think those workflows at a high level and kind of get those things done, like texting or calling someone. But what is a true smartphone? We'd like to see, right? We want to see a screen. One of the aspects of the smartphone, like I mentioned in a previous episode, is beyond calling and texting, right? How about calling an Uber? How about like you're getting bored in a meeting and you want to browse basically your phone and order something, right? So how do you go about doing those things, right? With all those capabilities embedded in your brain. That is the use case that we will use to understand how it will work, and obviously along the path highlight the constraints in terms of our current understanding of the brain. Now, one of the interesting things that we need to understand is that we do not actually need our eyes to see, which seems like, I mean, we do need our eyes to see, but the way we see things are not the way we visualize them because of our eyes only, right? Because our eyes are more like the lenses in a camera, if you think about it. So there is this visual cortex, right? So eyes capture, right, the light and the image, and then there's an organ called abbreviated as LGN, and then there is this complex visual cortex pathway, like you see here, right? So the information gets processed through that pathway, and there are, like, as you see, there are few different areas within the visual cortex, each handling different aspect from the captured image, right? Now, what has been done in some blind people is to bypass the eyes, right? Because if eyes are only capturing the light and other key characteristics that are then used by our brain to create the image of what the eyes are seeing, researchers and scientists have tried using cameras that feeds directly to the visual cortex, right? So if there's something that feeds to the LGN, bypasses the eyes, some form of rudimentary vision can be generated in blind people, right? And it's the same concept that will be leveraged if we want to have that capability. There is no other way, actually. But as you can imagine, to have that level of sophistication where you can see the entire phone screen bright and clear, the level of understanding that you need to have of the entire visual cortex is extremely detailed, and that's one constraint, right? But as you can see in this architecture, right, you will have that device embedded right before the LGN, and it basically integrates with the LGN, right? So, and then this device interacts with an external device, right? The external device that we have kind of touched upon before, right? And this external device may or may not have a screen, but it can project a screen to this device embedded and latched onto the LGN pathway, right? So that's the architecture. And one key thing to understand is that there will not be just one chip embedded. There has to be multiple devices, right? So for example, visual cortex then communicates to the frontal lobe via the parietal lobe. So all that pathway needs to be captured by intermittent micro devices, right? So that's one aspect in the architecture. There will be more than one devices, but let's get back to our example that we are discussing here. So this device then captures the screen. Next, obviously, it kind of communicates the visual of that screen to the frontal lobe. Now remember, we discussed how we can actually train a customized AI, right, for each customer, and that kind of gives them a little bit of telepathic thing where if the training has been proper and accurate, then they can think of keywords and the associated signals will be interpreted, and the interaction may happen based on that. So now that the customer sees the screen, there will be that interaction aspect. So we see, then we act, then we see, then we act, right? So for example, let's look at this workflow in the context of this architecture, right? So we start with, okay, I want to see my phone, right? Show phone. The specific neurons that get fired when the customer thinks show phone, right? And then thinks about the screen of the phone, like the phone getting unlocked, have been captured through training, just to remind, right? So how it works. So you see phone, shopping, right? You want to shop, open the app, you think about a specific app. Every app on your phone has been mapped to a specific pattern of neurons firing, right? Then search, you can type, a technology that's already actually being leveraged in people with disability, where they can type by thinking. You look for, you browse the product. So everything can be done through thought, right? Because it's actually being done in a rudimentary format right now. It will be more sophisticated, but just imagine the amount of training for each specific individual that needs to happen, because not all of us think in a specific language or think in a specific way. When you think about an app or any activity that we are going to do, go back to the motor neuron example, right, from the previous episode. So that's another challenge. But this workflow, which is basically see, act, see, act, see, act, works in tandem with this device and a central processor embedded in the front lobe, right? Kind of bridging the gap between see and act, see and act, right? And as you can imagine, there has to be at least 2 more devices, right? One embedded after the LGN within the visual cortex, at least one in the parietal lobe, right? That communicates with the centralized frontal lobe chip to make this workflow happen. Well, it may sound futuristic, but that's the only way actually to do it. If you want to do it in the future, the constraints I have already mentioned. I think the most important ones, one is that the understanding of human brain is at a very, very rudimentary stage right now, considering the capabilities that we are planning to develop. That brings us to the end of the 4 episodes focused on brain-computer interface in Maverick Monday. Thanks a lot for watching. I'll see you again tomorrow.